Okay, good morning again. Recording started. Good. So, we are already at the third lecture. So, do you have any question so far related to everything? First, I want to just confirm that I am checking about the possibility of scheduling the first exam before June 9. It will be not much earlier in any case, because we are supposed to teach until, May 20, more or less. I hope I'll be able to give you a reply quite soon, because I have also to find a room, which is not easy. It's not easy because until the end of the lectures, everything is fully booked. So I am struggling with the logistic and the formal constraints. With the formal constraints, I trust that we can find a way. With the room, I'm checking. I hope I'll be able to give you some additional information next week. Okay. So how is this week organized? Today we are teaching in person, and of course on Thursday it will be online. On Thursday, I plan to start with an introduction to the practical exercises, but the introduction will be strictly connected to the theory. I try to explain better. On Thursday, I'm planning to introduce some concepts related to climate change assessment, and these concepts are a little bit, I wouldn't say nasty, but a little bit tedious if I explain them starting with theory, with writing on the blackboard, or etc. I think that the best way to learn these numerical concepts is to directly work with a spreadsheet or with some computation. So this would allow me to bridge ideally and in an efficient way what I want to say about computation, use of the computer, which is something that is very specific for engineers. I would like to try to bridge very efficiently this practical part with the theory. So use the practice to better understand the theory. So what is the moral of the story? While I usually suggest to non-engineering students that you may skip the lectures on Thursday, and also while I suggest to any student that if you are not interested in practical exercises, you may skip these lectures. This is not my advice, but just to help you to get better organized. Next Thursday, I would say that if you skip the lecture, you are also missing, I think, an aid to better understand what I'm saying. So what is my suggestion? Attend on Thursday. Okay, this is my suggestion. And of course, my suggestion, you are not obliged to follow it. Absolutely. Okay, now, where are we today? I taught online on Thursday, and let me share the screen. We got basically, we started the lecture on the Earth system, and we got to a slide. Just 1 second, let me try to start the presentation. It's here. We got to this slide. We talked about various cycles and the spheres of the Earth system. We made a first attempt to better understand how the Earth system works, okay? And then we got here, basically, yeah, we got to this slide. But let me just go back a little bit, a couple of slides, okay? And what I talked about Thursday, which I think it is extremely important to understand what we are talking about, is the functioning of the Earth system, including climate, because climate is a part of the Earth system. So we talked about the functioning of the Earth system. We talked about non-linearity. We said that this is a bit concerning, the presence of non-linearity. It is something natural, so we shouldn't be surprised by that. but it's a bit concerning because non-linearity means that it's not easy to make predictions. Look, we are talking about adaptation to climate change, so we have to start from predictions. We have to understand how climate will behave in 50 years from now, okay? So it is a bit of a problem, non-linearity, and also non-linearity involves the tipping points. Let me just see if probably it's much better if I down the light a little bit. Okay, so I think this is probably a little bit better. And tipping point means, again, that it's not easy to make predictions, and tipping point means that the same system can have different equilibrium states and can shift from one equilibrium state to another, and the shifting back may be not easy, okay? And then we talked about tipping point in the social system. So even in the societal organization, there are some tipping points, okay? Think, for instance, of an election. An election may change the asset of the government of an institution. So think at the University of Bologna, the last election for director, it changed a little bit the organization, the internal organization. Depending on who wins, the system goes to a different state, okay? Think of an election, two candidates, candidate one, candidate two, and depending on who wins, this candidate then selects his co-workers and sets a strategy, a political strategy, a governmental strategy, which is perfectly fine. And then you have two equilibrium states, because usually any strategy tends to equilibrium, but they are different. And the shifting back may be not easy, okay? Because once that you organize the administration, once that you organize the apparatus of the society along a given track, then it's not easy to make a change. Sometimes these changes occur unexpectedly, and this means that for a long time you shift to another equilibrium state. Now, why I'm saying this? Because the impact of climate change, which we want to mitigate, adaptation means mitigation of impact. The impact of climate change depends on the interaction between the Earth system and society. If the society is prepared against a change, it's not a problem, the change. If the society is not prepared, then the change is a problem. So, to give you an example, very, very easy. If we get a drought and a decrease of water availability, okay? This is a problem if society is not prepared to cope with it. If society anticipated this and tried to get harnessed by finding more water because they were concerned by this, then it's less of a problem. So we have to understand this interaction between the Earth system and society. And also, if we look at the Earth system itself, the Earth system has different spheres, we know. So there is one sphere which is climate, we can say, like the atmosphere, okay? And then the sphere interacts with the land. With the land is represented by other spheres, like geosphere, etc. We have to understand this interaction because a given climate change may be a problem if the land has a feature, a specified feature. May not be a problem if the land has a different feature. Let me give you an example. Let's suppose that climate change changes rainfall amount, the intensive rainfall. You know from the media that we believe that there is an increase of flood frequency due to climate change. Floods result from the interaction of climate with the land. So let's suppose that indeed there is an increase of intense rainfall. Okay, this increase of intense rainfall does not necessarily cause a flood. It causes a flood only in the river basins which are weak, which are less protected, which are more prone to floods. If you have a change in rainfall in a basin that is not really prone to floods, this is not a problem. For instance, think of Italy. In the past 20 years, okay, from after 2000, we had an increase of floods. But which floods? Not the big floods of the Po River, the Tevere River, the Arno River. we had an increase of the so-called small floods, flash floods in small basins, which means that with the current climate change, it's more of a problem for small basins, not for the big ones. Why? We will talk about it. Okay? There is a reason for that. And this reason we have to understand if we really want to be able to design climate change adaptation. We have to understand the interaction between these spheres of the Earth system, including society. This is what I want to emphasize on the lecture of the other day, of Thursday, last Thursday, where I said we have to take an holistic approach. But on Thursday, I decided to take a reductionist approach because I wanted to understand any single component. Holistic means that we have to look at the whole system, the whole Earth system, the whole set of the spheres, including society. This is something that we have to understand if we want to move forward with solutions. Good. Now we have to make predictions, I said, and predictions are done, unfortunately, with mathematical models. These are not the only one solution. Mathematical models, it depends on the attitude of the students. There are some students that get excited when they hear about mathematical models. They get really excited because they like numerical computation. They like the idea of solving the problems by taking an analytical approach. Okay, there are other students who get really bored by this term of mathematical models because they think probably that mathematical models are something tough, something difficult to understand. Or there are some students who think that mathematical models are not reliable. I have to say that when I was a student, I was really concerned and annoyed by the term mathematical models because I thought that it was something that it was really difficult for me to understand, difficult to get in. And and in any case, whatever is your opinion, mathematical models are today a fundamental part of engineering, and not only engineering, also social sciences and humanities, because they are a good tool for making predictions. Here you see a kind of subdivisions of models in categories. I'm not going into the details now. In the slides, you see some more details. I prefer to forget about these details for now because we will have the opportunity to talk about model types later on. But there is one thing that I want to say. And you see on the screen a category which is called empirical models, which is opposed to process-based. What's the difference? Empirical models are perceptual models, are still mathematical models, but in a way they are very close to expressing in analytical terms our perception. What does this mean? That we have an opportunity to make prediction, which is the perceptual prediction, like I expect something, basing on what? Basing on my expert knowledge. So I may say, I expect that today will rain again, but not because I looked at the forecast of the weather, because I look out of the window, I see several clouds, and then I earn a perception. This kind of prediction is extremely important. So even if we trust a fully mathematical approach, we have to make sure that this matches with our expectation. And this is the role, the specific role of the engineer, but I would say that it's the specific role of anyone who makes a prediction. Anyone who wants to make a prediction should elaborate an expectation first, like an objective expectation. Like, I think that climate change in 2050 will have, I am expecting some features, okay? Like, I'm not expecting that the problem is naturally mitigated in 2050. This could be your expectation, okay? And then when we write the mathematical model, we have to use this expectation in order to elaborate our prediction. And whatever is the category of the model you use, you have to make sure that when elaborating your prediction, you use all the available information, all the available models. You have to gain a good knowledge of the process, a good knowledge of the problem, a good knowledge of the question mark you are trying to answer, and then you have to use all the available information. This is also very useful for an engineer, because if you make a mistake, as I said, if an engineer makes a mistake, as I said, I think also last week, then you have to prove that this mistake was done in good faith, that anyone instead of you could have, which tried to make the same prediction, could have made the same mistake, because you used all the available information. Okay, this is an issue that I really would like to point out. When you get involved in a responsibility as an engineer, as a social scientist, as a medical doctor, you have to make sure that you used all the existing information to elaborate your prediction. And then we have these several different models. And I just wanted to say that the perceptual prediction is very important. And you have to make an effort to be objective in this perception, because usually when we make prediction, not only, I mean, people tend to, in a way, unconsciously, to reject the predictions that turn out in a very bad outcome. This is known as, I don't remember the term, I will tell you, but it is a common bias, okay? Like, for instance, you think of the current war between Russia and Ukraine, and when we make a prediction, we tend to say that it will be at the end a positive evolution, not a global involvement, etc., because we try to reject the idea that this is badly evolving. So we have to make an effort to avoid the bias. Okay, and now let me skip this slide, okay, and let me also skip the issue of uncertainty, because we will have several opportunities to talk about uncertainty of the predictions. Let me just say, as I probably already said to you, that uncertainty for the engineer is something that is extremely relevant. Engineers, but anyone who makes a prediction should be aware of the uncertainty. And uncertainty is not a problem if you are aware of it. Okay, we are used, as I probably already mentioned to you, to make decisions every day of our life, and we are unconsciously used to deal with uncertainty. Okay, we know that when we take a decision, we know usually what may be the outcome, the impact of uncertainty. Again, now I just want, with this slide, and if you look at the lecture, I just want you to be aware of uncertainty, and then I anticipate that we will have the opportunity to talk about it. Now, let me spend a few words before moving forward with something probably more exciting. Let me spend a few words about the perturbation of the system, like climate change. Climate change is a perturbation. And the Earth system is exposed to perturbation of any kind. So we know that we can be impacted by meteorites. We know that the solar activity may change, and therefore more energy or less energy may come to the Earth. And what I want to say is that we live under the perception, because also we like this, that the Earth system is naturally in equilibrium, until the humans came and probably introduced perturbations. So this is our common perception. Nature as something that is in equilibrium, nature as something that is very positive, that is nice, and humans are responsible of perturbations. So let's remove this idea, if we have it, because the Earth system is never in equilibrium. And if we look at the history of the Earth, how the Earth was formed, and how the Earth will end its history, we understand that it's a sequence of transitions, you know. So, for instance, let me give you an example, which is also exciting. We basically took enough evidence of the past presence of water on Mars, a lot of water, really a lot. How did we gain this evidence? First of all, through inspections. The minerals that were collected over Mars contained particles of water. But more than that, it's the shape of Mars that clearly highlights the presence of valleys, the presence of basins, the presence of forms that were shaped by water. And it is really nice also to try to understand these valleys, these rivers, these fluvial valleys, try to study them in order to understand what was the amount of water there. And indeed, the scientific publications confirms that there was a lot of water. So the question is why water disappeared. And one of the theories is that Mars had previously an atmosphere, and this atmosphere was protected by the magnetic field, because on the Earth we got evidence that the presence of the magnetic field creates a screen against direct solar radiation. I'm not an expert of this, so maybe I'm not using the correct terms. If you make a search on the web, you can understand some more. So basically, the magnetic field protects the Earth and the atmosphere by the direct impact of solar radiation, which is dangerous for life and has the power also to destroy the molecules of water. So basically, the idea is that on Mars there was a magnetic field, there was an atmosphere, and then with the magnetic field stopped. Why? Because the magnetic field is originated by the movement of iron in the nucleus of the planets, and when the planets becomes older and older and older, of course, the nucleus gets colder, colder, and colder, which means that after a while, this movement of fluid stops. And then the magnetic field stops, the atmosphere becomes directly exposed to the solar radiation, and which means that the atmosphere is destroyed and the molecules of water are separated into hydrogen and oxygen. And this is probably what we think happened on Mars, which means that it will happen also over the Earth. And when? Billions of years. So we are not much concerned, but this is to say that for sure, life on the Earth is not going to last forever. There will be an end of the story. And this proves that the system is not in equilibrium. It's just in transition, and it's exposed to perturbation like volcanic eruption, impact of meteorites, and this is another interesting story. On Mars, the interpretation of the surface is made difficult by the presence of the craters of the meteorites. There are millions of craters which are still there because there is an atmosphere, there is no movement of water, so the shape remains conserved for a lot of years. And then we can understand that Mars is full of craters by meteorites. On the Earth, we have some remains. We can identify some big craters that are witnessing that also the Earth in the past was hit by meteorites. What is the moral of the story? The moral of the story is that planets are exposed to impact of meteorites, and this impact can be destructive. So also the Earth, sooner or later, will be impacted by other meteorites, and there is nothing that we can do. And the bad of it is that we may learn some couple of years earlier that in 2 years we will have a big impact in a predetermined part of the Earth, but we will not be able to understand what will happen afterwards, because it's like a big and massive nuclear bomb which may change the inclination of the Earth's axis, which means that the climate will change abruptly in an unpredictable way. So this is just to say that we live in a system that is exposed to perturbation, but the time scale matters. We are not interested in the time scale of billions of years. Like Mars has many craters because we can see the traces of what happened during 10 billions of years. We are not interested in that because we are interested in the time scale of the human life, which usually for us, it's like a couple of thousand of years. We are not much interested in understanding what will happen in 2,000 years from now, because it's not relevant to us. So this means that there are concerns for the Earth system that are not really implying concerns for humans. And in 1 billion of years, there will be again human life on the Earth. Who knows? Maybe yes, maybe not. So we are not very interested in knowing that, but we are interested in knowing the functioning of the Earth system. So we have to understand that perturbations are something usual. Human impact is a perturbation, and we have to understand the Earth system as a system that is being able to evolve, is being able to react. Why nature is able to react to perturbation and to compensate for them? Because otherwise there wouldn't be life on the Earth. If life, so nature intended as life, wouldn't be able to react to perturbation, there wouldn't be life on the Earth. Okay? Because life has been exposed to several perturbations. So what is the meaning of this message? The meaning is that human impact is one of the perturbations to nature and to the Earth system. We don't have to be excessively, we have to be concerned, but we also have to be aware that there must be solutions. And we have to identify these solutions, the solutions that help nature, the Earth system, to recover from perturbation, to maintain an equilibrium, which in the short term is indeed an equilibrium. So there is no equilibrium in the long term, but in the short term, there is indeed an equilibrium. The equilibrium is what we can see every day during our life. Okay. Here, as an example of perturbation, there is the variation of the magnetic field. And if you're interested, this is not a matter for the exam. Try to have a look on Google to search information on the reversal of the magnetic field. We have evidence that the magnetic field of the Earth reverted in the past, meaning that the north switched to the south and vice versa. And there is an active research field on the causes of this reversal, which may happen again. Because as the iron in the nucleus is rotating, the magnetic field can take a direction or another direction. It is the same movement, can put the north above or below, depending on how the magnetic field is generated at the beginning, with dependence also on the initial condition, depending on causality. And therefore, now there is, as I said, an active field of research trying to predict if the magnetic field could revert again in the near future. And what would be the consequence? Not really so bad. There would be changes in climate. You have to change the compass, of course, and to change the orientation of your compass. But it wouldn't be so bad. But in any case, it would be a significant perturbation. I found it exciting because I had the opportunity to chat for about 1 hour with a person making research, an old person who spent his life to make research on this. And it was an interesting conversation. And also to understand the unknowns, because actually they still don't know what could be the cause of a reversal of the magnetic field. Okay, this is just a list of the disciplines of Earth system sciences, and basically you can identify a discipline for each sphere, or more than one discipline for each sphere. It's just an interesting information. Also, keep in mind that there is intensive research activity organized along these disciplines, and there are international scientific associations promoting research, promoting meetings, conferences, and promoting publishing journals, so publishing research articles on that. It is indeed something that is very topical nowadays for climate change, but for many other reasons. Okay, now let me share the screen, and let me pass to the next let me highlight the blackboard. Okay, let me keep this screen. This on the screen. In the room, there is on the screen the Teams window, but from now on, for the next hour, you shouldn't look at the screen there, but on the blackboard. And I like once in a while to teach on the blackboard because I think for the people that are in the room, it's more productive. And I would like to change the camera and to focus on the blackboard, so also the people perfect. So if you are attending online, you can see the blackboard now along with my face. And what I want to do in the next hour is to start introducing some technical discussion, and it will be very smooth at the beginning, okay? So I will start not really technical. It will be, as I said, very smooth, and it will lead us on Thursday to also make some computation. And so I hope also to resolve the concerns of those of you who think that the start of my lecture was a bit too trivial. And but again, I will be very smooth in that. Now, about what I'm saying now, there is still no lecture on my website. It will be there quite soon. I just wanted, it's under preparation, but I wanted to anticipate the physical lecture to the writing because I want to make sure that it is the document that is shaped according to the physical lecture rather than vice versa. And I just wanted to, given that this is a new lecture, I just wanted to make this kind of workflow. So we are talking about climate change adaptation. And adaptation to what? Adaptation to risks induced by climate change. There are many risks that are potentially connected / originated by climate change. I think that we may discuss these risks by making reference to the National Recovery Plan of Italy, who financed several research projects dealing on topical issues for our societal asset, our societal community. So there is a research project that is focusing on energy production. There is a research project that is focusing on the space, so satellite monitoring from space. And there are several of these research projects, and there is one that is focusing on environmental and anthropogenic risks, with the attempt of contributing to mitigating the impact of these risks through mitigation of the risk and adaptation to the risk. So the purpose is, we know that there are some risks that are impacting Europe, societies. The National Recovery Plan is financed by the European Union. So we know that there are some risks that are impacting European society. We want to mitigate their impact, either by eliminating the risk or either by accepting the risk, but adapting to it. This particular research project is developed in the form of an extended partnership, which means that interested parties have to submit a proposal with a research plan and had to propose a team that had to include academies and industrial partnership and also institutional partnership like the civil protection, etc. We are talking about risks. And there was a constraint that 100% of the fund should be spent for research activity focusing on climate impact. This is a strong constraint by the European Union. The national recovery plans have to focus on 3 issues. It's climate, another one is digitalization, and the third one I don't remember, sorry for that, but you can easily find it. And in this particular case, environmental and anthropogenic risk research project was asked to spend the whole money on research related to climate. This was something that some scientists didn't really like, because if you think about, for instance, earthquakes are a huge risk for Europe and for modern society, which is very weakly related to climate change. Anyway, what are the risks that are being considered by this partnership that won this, submitted a proposal and got the financing? So these risks are, first, water. Second, hill slope instability, which means landslides. Third, earthquake and volcanoes. Fourth is environmental risks, which means contamination of like spread of contaminants, etc. It's a big category. And then 5, urban areas. These are more, let's say, specific risks. And these are exposed context. Exposed contexts. Okay, so urban areas. 6 is critical infrastructures like bridges, for instance. Infrastructures like bridges. 7 it's societal assets like institutions, etc. And there is overarching research activity. This is overarching on climate services. What is climate services? Climate services means predictions about future climate and predictions about future risks, future impact. So it's not only climate, it's also analyzing this interaction between climate and the spheres, interaction between climate and society. Okay, these are the risks. And we are supposed, yeah, there is a question in the room, please.
Yeah, no, I wanted to ask if it's possible to switch on the light because I can't see that.
Correct.
Thank you. Thank you.
A little bit better. I need to use only this one because it's taken in the video. Okay, so why I am providing this list? For your information, I'm referring to the National Recovery Plan of Italy because I am involved in this research project, so it's easier for me to follow this scheme, which is quite typical. I mean, if you browse on the web for climate-related risks, you find a similar list. And I am referring to this list or to another alternative, it doesn't matter, but I think we have to be fully aware when we talk about climate change adaptation or of what are the risks that are connected to climate. And according to the National Recovery Plan, this is the list. I mean, there is this category here, which is a bit borderline. But on the other hand, given that the project is focusing on environmental and anthropogenic risk, we thought that this was something for Italy that couldn't be ignored, and something that may be related to climate in a weak sense, meaning that what is the problem? What could be the major problem? the contemporaneity, the exposure to several risks, the multi-risk context. So we thought that indeed earthquakes are not directly caused by climate, even if there is some research that investigated the linkages between climate and earthquakes. There is some research on that. And especially for earthquake with reduced intensity, there might be, they found some connection. For instance, think of less rainfall, drying of the soil, and therefore a decrease of the water pressure into the soil. Water gives a lot of pressure on the contours of water. So if you decrease this pressure into the soil, you may have small earthquakes, like some shaking of the soil, which reacts to the decrease of the pressure. It's difficult to explain a big earthquake, which is caused, by big shifts of the continental masses. It's difficult to explain a big earthquakes to find a connection with climate. But in any case, I can provide an example where an earthquake caused an increase of the other risks that you see listed here, because the earthquake that occurred in 2012 in the Emilia-Romagna region caused soil liquefaction. And therefore, there were problems with the soil liquefaction, collapse of building, not for the earthquakes, but for soil liquefaction. So slope instability or instability in general. And then the earthquake caused a problem related to water because the soil liquefaction undermined the stability of the levees of the rivers. And therefore the land, the territory became more exposed to floods after the earthquake. And so you can see that there might be a linkage. So this is how we explained the inclusion of this category of risks there. Anyway, we have to mitigate these risks, the impact of these risks. We have to adapt to these risks. Adaptation requires money, requires resources, and these resources, especially in countries with a high public debt, may not be readily available, which means that we may not have the means for reducing all of these. We have to identify priorities, what is more urgent. Just to say something more, one of the problems with climate actions is that we don't have the resources. Climate actions require a huge social cost, and which is especially borne by the disadvantaged categories. And so we need funding, we need governmental funding to limit the social cost. It's not easy. It is absolutely not easy. And this is why there is some inertia. There is some resistance by the institutions. It's not a bad will. It's rather the concern because if you redirect resources on climate actions, then it means that there is a decrease of resources for other actions, other type of actions, other types of social interventions. So what is the moral of the story from our point of view? We have to be able to estimate the priority of these risks. And how can we estimate the priority? The usual way is through the estimation of risk. Risk related to water. Let's find a number. Risk related to slope instability. Let's find a number. Whatever. For any risk, we need a number. if identifying a priority means ranking, and the ranking usually is made by numbers. We need a number. What I'm doing now, I am introducing what is called, let me delete here. I am introducing what is called risk-based adaptation design. Risk-based adaptation design. Which is a specific branch of engineering, but actually it's interdisciplinary. And it's a topic that is relatively new. If you look at the terminology and the theory was founded about 20 years ago. Or let's say was organized. They started to organize the theory of risk-based adaptation design and risk estimation about 20 years ago. It's a relevant problem. So, for instance, during the pandemic, people were discussing, because the pandemic basically sorted the effect of reducing the attention of people and the attention of institutions to climate change. And there were some researchers who said, actually, climate change is a risk to humanity that is greater than the risk of pandemics. But is this true? We need a number. We need to say, okay, the risk of pandemics in the future, because it may happen again, we know. Virologists were saying this already. I heard, I spoke with a virologist in 2019, and she said, look, I think a pandemic will come soon because there are all the premises. A global pandemic, she said, I think it is a very relevant risk. It will come soon. And I was amazed because we spoke together and I didn't know this person. We shake hands and she shake the hands with a lot of people. And then she said, where is a toilet? Because I need to wash my hands because too many hands I shaked in 2019. And it was spring 2019. Okay. Just to say that we need numbers. We need to understand if we have to spend money to get protected against the next pandemics, or getting protected against the next flood. So it is a big question mark, how to estimate risk. Okay, so how can we estimate it? How can we estimate this number? So the theory first identified the relevant drivers of risk. So the theory said, okay, we need to identify what is determining risk, and then we can think of how assessing each driver. So this is how we usually explain something in physics, for instance, in engineering. We try to get a perceptual knowledge of how the system works. We make observations, we make assumption, hypotheses, and then we build on these premises models to explain the process. Okay, so what is determining risk? A first conclusion was that risk is proportional to the value of the exposed assets. Drivers of risk. Drivers of risk. Okay, first, E, value of the exposed assets. forgot to say. First of all, we have to focus on an event that is causing risk. Okay, so first there is drivers of risk depending on the event. So if we want to estimate the risk originated by an earthquake, the event is an earthquake. Okay, and then the earthquake risk depends on the value of the exposed assets to the earthquake. If the event is a flood, again, the flood risk, a driver of the flood risk is the value of the exposed assets. So the theory applies to any event, to any type of risk, but of course, when we pass to the estimation, when we pass to the identification of the number, we need to focus on an event, okay? And we had a list on the blackboard first. Before a few minutes ago, we had the water. Water means droughts, floods. We had the landslides, instability, etc. So the value of the exposed assets is important. If there is no value, there is nothing exposed. If the earthquake occurs in a fully natural environment, and an environment which has no value, because the value is not only related to human issues, to houses, to industries, and a value may be also of a forest. If a forest is destroyed by an earthquake, this is a value that is lost. But let's suppose that something happens and nothing is exposed, okay? Then it's not a problem. So we don't have any problem with a flood occurring in a isolated area. What's the problem with the flood? Nothing. The flood is a problem if it destroys infrastructures, if it kills people. But for instance, if you think of the ancient Egyptians, the flood of the Nile River was considered to be very beneficial for irrigation, for fertilization of the land. So it was absolutely not a problem. So the risk for sure should be proportional, they thought, to the value of the exposed assets. Value expressed in what terms? So it is usual practice to use monetary terms. Pros and cons. It is convenient to use monetary terms because it is relatively easy to monetize everything. Relatively easy. On the other hand, you know the problem what is. The problem is that there are some values that may be intangible, like the human life. Okay, insurance companies are used to monetize also the human life. Still, it means that you are comparing the value of life with the value of a building or a bridge. Still, it's something that, so some people say, some scientists say, let's separate the economic damage from the intangible damage. Tangible means something that can be easily monetized. Intangible is something that it is not easy to monetize. You can monetize it, but still, And the human life is not the only example. It's not the only one. Think of, for instance, of cultural heritage. It's something that can be destroyed. Think of, for instance, churches, paintings, or historic buildings. It's something that can be destroyed by a flood, by an earthquake, and how to give a value to cultural heritage. Cultural heritage is important for the economy, for the tourism. It's important also for the feeling of people. There are some people who feel really, who give a very high value to cultural heritage. And also we give high value. Think of something that destroys the environment where you grew up. It is something that hurts your feelings. It's not easy. But anyway, the usual practice is to measure the value of the exposed assets in monetary terms. Okay, good. So it means that E can be expressed in billions of euros or something like that. Okay, and it is varying in the range 0 plus infinity. Here the range of E is 0 plus infinity. Square parenthesis means that 0 is included, and round parenthesis means that the other extreme of the range is not included. Okay, good. And then what could also determine the risk? Think of this. You may have a land that is highly exposed. Look at this term. Okay. Highly exposed, but it is very protected. Like I am protected against earthquakes because the buildings, the infrastructure are designed to resist to the most violent earthquake, possible earthquake. So, I mean, if the land, if the societal system, if the environment is well protected, think of floods, a river with huge levees, okay? So that they are designed to be so high to resist to every excess of water. So the land is very protected, is well adapted. Then there is no risk, even if there is an high exposure. So the deduction was that we have to introduce a second driver, which is vulnerability, V. Vulnerability measures the level of protection against the risk. Level of protection. What could be a range for vulnerability? The idea was to fix a constraint for V to vary in the interval 0, 1. 0 means zero vulnerability. So risk should be 0 if V is 0. 1 means full vulnerability, which means that everything that is exposed, if the event occurs, is destroyed. It seems like a good idea to introduce this range of variability of vulnerability between 0 and 1. Okay? Okay. And then, are we done? No, because, I mean, I may have country, a land that is highly exposed, which is highly vulnerable, so vulnerability is 1, but if the event doesn't occur, nothing happens, risk is 0. So if I have a land that is immune by earthquakes, let's suppose that this is possible, okay? We can say, for instance, let's think about floods. There is no river, there is no water, so it's impossible to get flooded. So in this case, vulnerability against flood is probably 1 because people didn't think of getting protected. I have a high exposure. On the other hand, there is no risk. So I have to introduce another driver here, which is the likelihood of the considered event to happen. Is it likely that I have a flood here? Yes, no. Is it likely that I have an earthquake? Yes, no. So I need to introduce something, another driver here. Likelihood. So we may say, okay, let's put an L here. But how can I estimate the likelihood? How can I say that something may occur? I am expecting that a flood may occur or not. How can I measure it? So the idea was to measure the likelihood of the event through probability P. Probability. And here we are getting into something that is very technical, because I think that some of you had some backgrounds on probability. Let me write it down. Probability, am I still in the screen? Yes. Probability of the event. Do you have any questions? I hear somebody talking. Yeah.
So basically, we have the last two that are coefficients, and the first one is from a unit perspective, monetary terms.
Yes.
So if we have these three coefficients, is there like a system that considers the conversion of monetary terms in like something like a unit of value that can also take care of the problem that we have the invaluable, the intangible values or something like that? Is there like a experimental system like that is not monetary terms?
Okay, so the question was, we have here three drivers. One is expressed in monetary terms, and the other two are not expressed in monetary terms, but they look like coefficients. Okay.
So basically, they're numbers.
Yeah.
So.
Yeah. And then the question is, it's clear that if I move forward with this strategy, this setting, I get the result in monetary terms. So is it possible to also express the exposure, the value of the exposed assets in terms that are not monetary, so that we can also estimate the value of the intangible assets? Okay. Now, you are a bit anticipating my conclusion, so let me just conclude here with my discussion on probability, and then I will answer your question. Okay. This is a promise. Okay, so probability. As I said, probability, I think some of you already studied some probability during the bachelor, others maybe not. Probability, I know that is a concept that is sometimes hostile to students, so students don't like it, because usually probability is treated and introduced in very mathematical terms. It is not really easy to introduce probability without resorting to the mathematical basis of it. But we have a chance to do that, because if we refer to a specific application of probability, we may introduce probability by reverting the workflow. We first start with the purpose of it, what we need, and it's clear here what we need. We need to estimate the likelihood of something happening, and then we can explain how we compute this number, and then we go to the theory. So, and I'm not doing this today, I just want to introduce today the concept. So probability is needed to us because we need to estimate the likelihood of a flood, the likelihood of an earthquake, okay? And we need a number. So what it means, probability, it's clear. It means precisely likelihood. So I can, if I say, probably today will rain again, you understand what I mean. It is clear. Or probably the next election will be won by a specific party. It's clear. Probability is something that the meaning we know very well, okay? But when we pass to the estimation in numbers, this is always a bottleneck because we need a theory for it, okay? So now let me just anticipate that people, scientists, researchers, thought to decide that they thought it was useful to express probability again in the range 0, 1. So it's a coefficient, you are right, 0, 1. So let me express the probability of a flood occurring in this range, where 0 means it doesn't occur. 1 means for sure it will occur. If I make this reasoning, you understand that I have to refer not only to an event, a flood. So when I said probability 1 means a flood will occur for sure, what I am implying implicitly, a time frame in our context, like what is the probability that a flood will occur in the next year? What is the probability that a flood will occur in 100 years? So probability needs, in our context, to refer to an event in our context, because you can express probability in many different, for many different outcomes, like tossing a coin. But in our context, climate change, risks related to climate change, probability refers to an event, a flood or an earthquake or a volcanic eruption, and a time frame, time step. But it's clear what it means, 0, 1, and it seems very sensible. And think, for instance, at more examples. What is the probability of a flood occurring? Where? In Bologna, from what? The Reno River rather than the sewer system in the next year, you would say. Look, if I'm not very unlucky, the probability is not 0 because it may occur in the next year, but it's not so high, like, I don't know, 0.5, just to give. 0.5 seems very, I mean, a bit excessive, a bit in excess. 0.1, maybe. But if I say, and in the next 100 years, you think at it and you say, oh, 100 years, it's a long time, so the probability increases in this time frame. It may become 0.5. Okay, this is probability. So just think at this way of quantifying your perception of the likelihood of something happening. Now, if the probability is 0, the risk is 0, even if vulnerability is 1 and the exposed asset is a lot. And therefore, what could be the ideal way of combining these 3 drivers? Let me say, first of all, that for now we stop here with the drivers. You may think of additional ones, but let's stop here because this is what the theory of risk-based adaptation design determine. A question.
In the value of the exposed assets, is there also, or are there also penalty payments included? Because there have been like international agreements on what has to be done, and if countries don't reach those goals, they have to pay penalties. Is this included?
Actually, you are a bit anticipating, but the question is interesting because we are not discussing how they are estimated yet. I'm not discussing how vulnerability is estimated, but your question is interesting. The question was, is the value of the exposed assets includes penalties that have to be paid, like because a country didn't comply with international agreements. And let me make an example. There is the flood directive that was approved by the European Union in 2007 that sets some targets to be met by a certain time frame. Like, I remember that by 2015, the member countries were asked to identify the area that were exposed to floods. And they decided penalties if the countries didn't comply with these requirements. Actually, these penalties, I don't think they are related to flood occurrence. So I don't think they should be considered part of the risk. So I mean, the penalties are organized in a way, and then I give you the word, that they shouldn't be paid if a flood occurs. So the penalties are just to be paid independently of the occurrence of the event if the country doesn't comply. Do you have another additional question?
No, you just answered my second question.
Okay, perfect. Okay, and so it's not really included. And so let me just say that what could be the ideal model, I said, my question, to reflect the fact that risk should be 0 if probability is 0, if vulnerability is 0, no matter the value of the exposed assets. So the easiest way was to determine the risk as the product of the three, P times V times E. And then I didn't forget your question. This is risk estimation. Now, there was a question saying, then, the question didn't say that, but the meaning of the question was, then the result in terms of units of risk is monetary terms. Monetary terms. Because vulnerability is dimensionless and probability is dimensionless. While E is expressed in monetary terms. So, there might be alternatives, yes, there are alternatives. For instance, several researchers said, let's separate the risk, the monetary risk from the risk of loss of lives, and therefore you could express a risk in terms of loss of lives in terms of number of lives that are lost. So this is possible. It's not usual, and in general, as far as I know, it doesn't exist a scheme for putting together tangible and intangible damages. I don't know anything of that, while I saw some contributions separating the two things, like number of lives that can be lost, the risk of losing life from the risk of losing money. I saw some contribution separating them. I can also say that insurance companies are used to monetize everything, and therefore they put together everything. But you know, it is something that is questioned. And also, let me just anticipate that another key role of insurances, they can reduce the exposure, because if you stipulate an insurance covering the damage, then the exposure E decreases, at least for the monetary exposure. So I can get insured against a flood, and this is done in many countries. Instead of protecting the homes of people, they make sure that people don't lose their lives, and then they say, I'm not spending money for protecting you, but I'm giving you the money to get insured. So if you get a flood, then you get paid back by the insurance company. And this is something where insurance companies are really very active, because it is a good option. I mean, it's not reductive. So if you have to spend a lot of money to get your house earthquake-proof or waterproof, and let's forget the loss of lives, because in a way we are sure not to lose our lives for some reason. Like for a flood, it is easy. I can easily understand if my life is at risk or not. If I'm sleeping at the first floor, I can accept that the ground floor is flooded. It's not a problem. And then instead of making my house waterproof and spending money to make the house waterproof, I may decide to get an insurance, because it's maybe cheaper, maybe more convenient. Okay. Of course, we now understand how we can estimate this number. So we may refer to Bologna and say, okay, let's estimate the risk of flood originated by climate change. Perfect. Let's get the exposure, let's get the vulnerability, let's get the probability, and then we estimate the risk. And now let's refer to earthquakes, etc. It is not easy, because you understand how to estimate probability of Bologna to get flooded, and also think that probability refers to a time frame. So are we interested in making a prediction for the next 100 years or the next 10 years or whatever? and there is a lot of literature on that. And then you have to estimate the extension of the flooded area. So it depends also on the intensity of the flood. If the flood is a huge flood, then you get more exposure. If it's a smaller flood, you get less. And then vulnerability, how to estimate it? Because I talked about a LV that is much higher of what much higher. But it's not always possible to build a LV that is so high. In general, remember, there is no absolute protection against natural hazards. So there is no certainty against natural hazards. So you cannot say probability of an earthquake is zero, nowhere. And you may say that probability of a flood is zero, but only, in a desert area. If you refer to a social context, there is no zero probability of flood. Why? Because people live close to water, so it's impossible. If you live in a city, you are close to a river. You are exposed to flood because the flood can come from the sewer system. There is no zero risk of droughts, no zero probability of droughts, and there is no absolute protection. So you can make, a building that is earthquake-proofed, but if a huge earthquake happens, it may happen that a really unexpected earthquake occurs and your vulnerability is not zero. Flood, same thing. There is no upper limit to the value, to the intensity of a flood. It may happen a flood that never occurred in the history of the Earth. It may happen. And then, even if you have a LV, a much high LV, then the LV is overtopped. And then remember that when you are, in the case of flood, this is a paradox. If you have a LV that is very small, if it collapses, it's not a big problem. If you have a LV that is 20 meters high, it means that you get a wall of water inside the riverbed that is 20 meters high. If the LV collapses, it's a disaster. So sometimes adaptation may increase the vulnerability. You work for decreasing the vulnerability and you increase it. Another thing that has been noticed is that if you protect an area, the area gets more exposed. If you build a levee around the river, people feel safe and they say, okay, let me bring industries here, let me build an house of a very high value because I'm not concerned anymore by floods, there is the levee, and then the exposure increases. And if the levee collapses, it's a big disaster. And this is called the levee effect in the international literature. Actually, the levee effect has been known in Italy since 1930, 1950. Because when we started to raise the levees of the Po River, we realized that we were increasing the risk in case of a huge flood. So it was a well-known concept in Italy already almost 100 years ago, and then the international scientific literature proposed the levee effect as a big discovery like 10 years ago. People realized that suddenly there was this kind of paradox. In Italy, it was known already. This happens quite usually in science, especially in the national literature. For instance, the Russian literature anticipated the concept of probability and stochastics, the probability estimation, that became known in the Western world after 50 years. And so sometimes we are reinventing the wheel because especially in the national literature, there are some discoveries that don't become known to the world. Now it's more unlikely because there is more globalization also of scientific research, but in the past it was quite usual, and the levee effect is a nice example. Okay, now the problem is how to estimate these three numbers. So we will not focus much on exposure. We will say some concepts like increase of exposure, if I build a levee or if I make an earthquake-proof building, but we will not talk about how to estimate the value of a building or how to estimate the value of intangible assets. We will not talk about it. This is something that is dealt with, in economics, in social sciences. So we will not discuss about it. We cannot discuss everything. We will discuss a little bit vulnerability, but we need to discuss probability. We need really to discuss it. What does this mean? It means that if you want to study climate change, if you're interested in climate change, I'm sorry to say that you have to know something of probability. Because otherwise it is impossible, because we are talking about events that do not occur with certainty. So if I drop this chalk here, I know for sure that it will drop over the ground, and I can also compute the time it takes to get to the ground. This is something that is almost certain. There is still uncertainty because depending on the position of my finger, I need to measure it. So there is a measurement error in the position of the finger, and therefore there is some uncertainty, but it's practically negligible. But if I talk about earthquakes, if I talk about floods, this is something that is not certain. It is something that may occur, something that may not occur, and how can estimate the likelihood of it? Probability. But probability is not a difficult concept. It's very easy. You understand what it means. It's very easy. And I will try to make it for you very easy. On Thursday, I will show you how to estimate probability. But before we make the break, let me ask you a question. Let's suppose that I toss a coin. So there is a nice example of random events. Random means not certain. Okay, you can also say casual events. So there is two examples of random events that are used to understand what probability means, and I think they are more useful than talking about floods or earthquakes. And the two events are tossing a coin and rolling a dice. Okay, these are very. If you take any textbook about probability, they start with tossing a coin. I just want to tell you one thing, which is fun. A famous statistician that was Pearson focused on tossing a coin. He proposed some revolutionary theory in probabilities, and he wanted to estimate the probability of getting an head by tossing a coin, and decided to toss the coin 24,000 times. Don't ask me why 24,000. He decided that, or probably he got tired after 24,000. So let me ask you this question. In your opinion, what is the probability of getting an head when you toss a coin? Given that probability varies between 0 and 1, we already learned that. What is the probability of getting an head?
0.5.
0.5. Other opinions?
I would want to guess a little bit less because the coin could also like fall on the edge.
Okay.
So I wouldn't say like exactly 0.5, but
okay. For those who are attending online, because it's very interesting the two replies that you gave. One said 0.5, and another person said, I would say a little bit less because there is a very small probability that the coin remains between head and tail. I don't know how to say in English that it stands on the edge. I hope you understand me. Okay. Your observation is very pertinent because I should have said that we need to reject this outcome because we conclude by our perception that it's impossible. In fact, Pearson never, after 24,000 attempts, he concluded that it was impossible. So let's reject it, okay? But your observation is perfect. So at this stage, you agree that it's 0.5, okay? Can I ask you, how did you estimate the probability of 0.5?
We have two options.
Okay.
And we're estimating the probability of having one of those.
Mm-hmm.
And we have a single event.
Mm-hmm.
So we have two. I'm thinking in terms of number. We have one outcome over two possibilities. So
okay.
It's 0.5.
Because implicitly, you didn't say that, but you assume that the two events have the same probability mass, let's say.
Yes.
Okay, good. So the reply was, I have two possible results from tossing a coin. I assume that they have the same probability mass, let's use this term, and therefore I split the 1 by 2, it's 0.5, correct? Okay, other opinions on that? Okay, Pearson thought that he wanted to prove that, so he made the experiment. So there are two ways in which you can say that it's 0.5. Either you toss the coin several times, you make an experiment, and then you compute the number of heads over the total number of experiments. And by the way, Pearson had over 24,000 experiments. He got 12,000 plus 24 heads, so it was 0.5. Okay, so he demonstrated through experiment that it was 0.5, and this is a method. And actually, you don't need to toss the coin 24,000 times. Even if you toss the coin 10 times, you get very close to 0.5. 0.5 means if you toss the coin 10 times, if you toss the coin 10 times, the number of experiment is 10. If you count, the number of heads is 5, and then you make the ratio. Okay, number of heads divided by the number of experiment is 0.5. This is what Pearson did. There is another possibility that you make a reasoning, like a perceptual reasoning, like you did. Like, okay, I toss the coin, and my understanding, my perception is that the two events have the same probability, and therefore it's 0.5 and 0.5. It is the same reasoning that we apply with the elections. If we don't make a pool, we say it's very likely that candidate number 1 wins the election. And it is based on your perception. Of course, in this case, you cannot make the experiment. You cannot make the election several times. Okay, very good. In fact, the method that you used is called, let me conclude by saying this. The method used based on perception is called Bayesian estimation of probability. And if you look on Google, Bayesian probability, it's a nightmare, it's a forest, it's a jungle, okay? But we got to it very simply. So Bayesian estimation. Bayesian estimation. And Pearson method is called frequency estimation. Frequency estimation. And let me just write down the formula for this. If n is the number of tosses, and let's call it 1 is, no, sorry, it's not good. H is the number of heads, okay, then we can write the probability of H is equal to H divided by N equal 0.5. This is the frequentist estimation. Okay, let's make a break and take a coffee. Questions before we take 15 minutes break? Good. Grazie. Okay. Let me check if, yeah. Okay, so I'm not moving further forward with risk-based estimation design today because, as I said, I want to get into the topic very smoothly. So I'm continuing on Thursday, next Thursday online. I just want to emphasize that we introduced some simple but important concepts today, which you should make an effort to take into account, because this is really the basis of our discussion for the future. We will talk in the future about estimating these three factors: probability, vulnerability, and exposure, with some probably more focus on probability because it is the central part for us. I just want to stress, among the other concepts, that we made reference to a time frame, and a time frame for probability. So when we talk about probability, we have to define an experiment, and the experiment is, in this case, for instance, what is the likelihood of an earthquake in the next 100 years or the next 10 years? This is extremely important to keep in mind, that when we talk about probability, we have to define the experiment, how the experiment is, if we experience an earthquake or not, or the experiment may be tossing a coin. It is important that we define the experiment, the time frame, the various constraints, and this is what I really wanted to fix in your mind. But pay attention to the other concepts that we highlighted today. Okay, now to continue a little bit, to make a break after the break before passing to discussing again about climate change, and before I follow the other links that are on my website, I would like to watch with you this video, which is a way of taking a pause. I share the screen and the audio for those who are attending online, so everything should be available for you. It's not long, it's 6 minutes, and this is part of the geoscience videos. I think I already discussed with you last week. I make some confusion because I'm teaching 2 courses about climate change, so I hope that I'm not mixing my remembers. Anyway, if you look on Google for geoscience videos, you get to these resources, which are very interesting. They are open source, they can be shared, and there is a lot of information. The nice thing is that each video is followed by a question and answer session, and which helps in order to metabolize the concepts. This is not what we are watching now. It's not a matter for the exam, and it is just in order to give you an idea of what climate change means. And I propose that we look at this video together, and then I will give you another indication of a video that I suggest you to watch. They last about 5 minutes, so they are a good way of taking a break. Okay, so the first one, as I said, I prefer that we look at it together. And I leave the video moving, and if you have any question, we can discuss it.
We will examine some of the indicators that Earth is warming and the evidence that suggests that these changes are the result of human actions.
We have two learning objectives. First, we will discuss why many people think that recent climate changes are due to human activity, and second, we'll review some natural indicators of a changing climate. But before we can begin, we have to explain a term that gets used a lot during discussions of climate change. We need to introduce you to a temperature anomaly.
A temperature anomaly represents the difference between the measured temperature and a long-term average value. Climate researchers calculate long-term averages from data sets spanning 30 years or more. For example, this graph shows average annual global temperatures for each year since 1880. Rather than plot the actual temperature, the data are compared to the long-term average calculated for the last century. The zero line represents the calculated average temperature. Blue and red bars show the difference above or below average for each year. The red bars indicate positive temperature anomalies, the blue bars are negative anomalies.
Just on the basis of this data, you can see that it looks like temperatures have been getting warmer in recent years. But you wouldn't be the only one to think that. If we were to analyze thousands of scientific papers that discuss the relationship between climate change and human activity, we would find that 97% of them make the case that humans are causing changes that result in the warming of Earth.
In contrast, if you were to pose a similar question to the general public, you would find just 41% of people agreeing that climate change was happening and that it is caused by human actions. A lot of other folks either don't know or disagree.
So first, let's look at some of the evidence that has convinced scientists that we humans have caused global warming, and then let's examine some of the changes to the Earth system that support the interpretation of a warming Earth.
If we compare temperature anomalies over the last 1,000 years, we can see that recent temperatures have not been matched in the last millennium. The rate at which temperatures changed and the length of the warming interval in the 20th century are greater than at any other time in the recent past.
The reason for this temperature spike is related to a dramatic increase in the concentration of greenhouse gases, like carbon dioxide, in Earth's atmosphere. For much of the last million years, carbon dioxide concentrations were below 300 parts per million. But these values have risen dramatically as human population increased. Since the Industrial Revolution, the concentration of CO2 in the atmosphere has increased by 40%.
The science linking increasing concentrations of greenhouse gases to higher temperatures is well established among atmospheric chemists. Consequently, it should be no surprise that since 1850, the globally average surface temperature rose by 0.85 degrees Celsius, or 1.5 degrees Fahrenheit, or that the 10 hottest years on record have all occurred since 1998.
One reason why people find it difficult to make up their minds about global warming is that their views of climate trends may be influenced by short-term weather phenomena. But we need to understand that these types of seasonal or annual fluctuations are due to natural variability within Earth's climate system.
We must remember, too, that just because the global average temperature is increasing, some parts of the world will experience more or less warming than average. These spatial variations in temperature are represented on this map, which shows which parts of the world were hotter or cooler than average in 2013.
While most of the world was warmer than average, as indicated by the amount of red and pink on the map, temperatures across much of North America were actually below average during 2013.
If global temperatures really are warming for good, then these changes should affect many elements of the Earth system. Let's concentrate on two topics for which we have a lot of evidence: the distribution of snow and ice, and the characteristics of the world's oceans.
As you might expect, with increasing temperatures, we see a decline in the volume and aerial coverage of sea ice. The Northwest Passage, a cheaper, faster shipping route from the Atlantic to the Pacific Oceans, may soon become passable during Arctic summer for the first time in human history.
About 1/3 of Earth's land surface, almost all of it in the northern hemisphere, is covered by snow for some part of each year. Across the northern hemisphere, the total area covered by snow during March and April is less than in the past decades, and it is melting earlier than it did previously. Since the late 80s, there has been twice as many years when snow cover was below average as when it was above average.
The total volume of glacial ice on Earth has declined steadily for several decades. The 1980 photograph on the top left shows the end of the nearly 50-meter-high Muir Glacier in Alaska. The lower image, taken 23 years later, documents that the glacier has retreated more than 2 kilometers and has thinned by several hundred meters.
The graph in the lower right shows the cumulative mass balance of 3 U.S. Geological Survey benchmark glaciers from Alaska and Washington. Negative values indicate a net loss of ice and snow compared with their condition in 1965.
Some of this melting glacial ice is ending up in the oceans and contributing to rising sea levels. But the main cause of the rising oceans is the thermal expansion of warmer ocean waters. The graph shows the global sea level anomaly as measured by tidal gauges and satellites. During the last century, the average sea level has risen by 1.7 millimeters per year, or about an inch every 15 years.
The temperature of the waters in the shallow ocean are increasing, just like temperatures on land. Changes in sea surface temperature vary regionally. Much of the world's oceans have seen surface temperatures increasing by 1 to 2 degrees Fahrenheit since 1901. Some areas have increased by more, while other areas have actually cooled.
August 2014 was the world's hottest August since record-keeping began in 1880. Data suggests that this pattern will be repeated in future years. While there may be cooler years or regions, the general trends are for higher temperatures and sea levels, and for less snow and ice.
We had 2 learning objectives. How confident are you that you can successfully complete these tasks?
So for the learning objectives and the following quizzes, I leave to you the opportunity of exploring the end of this video. After watching this video, I suggest you to watch another one taken again by Geoscience Videos, which we are not watching together, but I suggest you to watch it because it gives a perspective on the natural variability of climate, ice ages, and the climate cycles. It is an interesting okay, it is an interesting perspective. Another perspective on a feature of our climate that we need to know and to get experience about. A couple of comments. Actually, the video is, I think it was prepared in 2015. It is not very recent. It doesn't include the latest data on temperature. And also the statistics that were presented, I think, are a bit old, and depending on the pool that they are based on, they can vary a little bit. And in particular, I'm referring to the general public. I think in the United States, people skeptic about human influence are about 35%, not 41%. But it depends, of course, on the context, the area, and the way the pool is carried out. You shouldn't be surprised by the fact that there is this striking difference between the opinion of scientists and the opinion of the general public, because the question is usually not clarified enough. I mean, just asking the question, are you convinced that humans are contributing to a changing climate? The reply that you are expecting is, of course, different if you refer to scientists and the general public. If you don't specify some more about the question. And in fact, the way the survey is done for the scientists is just by counting, it's by counting the scientific papers that negate the human influence on climate. And therefore, they are really few, because there is, I mean, from a scientific point of view, there is no point in negating the human influence on climate. The question should be posed in scientific terms. If we want to get more details. For instance, one may ask to what extent the human are contributing to a changing climate, and different alternatives should be given, like definitely or dominantly, almost dominantly, or more or less the same as natural variability. So it should be better specified in scientific terms. If we count the papers that are negating the human influence, I am surprised that there is 3% of papers that negate the human influence, because of course there is no point in negating it. While for the general public, a generic question is more appropriate, and the general public replies by personal feeling. It's not a statistic that is computed on evidence, on data. And so it is indeed important that when we present these statistics, further details and metadata about the statistics are given. Anyway, I just wanted to emphasize that this is a relevant question. So to what extent we are indeed contributing, which has an effect on adaptation measures. And I think also having a look to natural variability, to evidence of natural variability, helps in better understanding what is the context and what is the extent of human influence. Anyway, let's move forward. And now let's go back to the list of the links in the website. Let's move forward in what terms? In better understanding the next question. So evidence of climate change and mechanisms leading climate change. Let me share the screen and go to my website. So the next link here, it's just 1 second. It's sustainability in the 21st century. This is a link for you to read. This is individual studying activity. It is something that it's, let me just check it before saying that there will be no questions in the quiz. I think I can safely say that. Yeah. I can safely say that. So this is a lecture which is for you to read for your personal information, relevant personal information. And I think we will discuss later on about this last section, the bottom-up approach for risk management. We will discuss again this. So if you read it, that's fine, because this is an introduction. But we will have other opportunities to discuss about this part. And for the rest, I think it is something very useful for you to understand what is sustainability. It is a term that is a buzzword today very often, and it is used like climate change without a full meaning of what it means. So I suggest you to read this lecture because I think it is very relevant for its connection with climate change. So when we refer to climate change adaptation, we have to focus on sustainable solutions. And again, this is not material for the exam, it is something for you, okay? Now, let me introduce, I don't follow the chronological order, so please be patient with me on that. Let me focus on better understanding the climate change problem. And let me check if there is a PowerPoint. Yes. Let me open it. And let me pass in presentation mode. Good. So this is a step forward in understanding climate change, how it manifests itself, and what we need to learn about it. And I make reference in this first slide. Let me just go back to the web page. 1 second. It's here. I make reference at the beginning to sustainability, climate change. Yeah, there is a question, please.
I have a question to the risk factor.
Yeah.
Is this purely academic, or is this actually used to, I don't know, counter references to investments, the necessary investments to reduce these costs, or is this right now just an academic value?
You mean this framework that I introduced for risk estimation, risk assessment?
Yes.
Yeah, no, it's not academic. It's actually used. And the insurance companies are really working every day with it. And there is a lot of interest, and I very often get requests from insurances to either provide consultancy or names of engineers that are expert in risk assessment, because they want to hire people to work on this. It is very, very topical and practical.
Okay, but only by insurance companies, or is this used by governments as well to?
It is used also by government as well. Yes, yes, and it is in a systematic and scientific way. It is mostly used by the consultants of the governments and by the insurances, but it happens quite frequently to receive from institutions requests. For instance, I'm frequently asked to provide a consultancy on the solutions for adapting to drought risk, because usually institutions don't get easily oriented in the estimation of probability. They know the exposure, like water boards, they know the damage, they know the financial damage they may experience if they get to day zero. Day zero is a nightmare for a water supplier. It means the day in which they have to just close the taps, which may happen. Like the water boards here in the Emilia-Romagna region are much concerned by day zero. In South Africa, in Cape Town, they got very close to it. So the water boards come to the academia and to the engineers by saying, I know what is the damage. I know what happens to me because it's a collapse if I get to day zero. I want to know the probability that this may happen. And what is the unknown is prediction of future climate. So I hope I answered your question.
Yes.
But it is really very practical. And this is, I mean, in this course, I make an effort to focus more on technical issues rather than scientific, purely scientific. Of course, it is nice and useful to make a bridge of it. So now I'm opening a lecture on the climate change problem, and I'm trying to understand the science of climate change. But I'm trying to make an effort to focus on the technical issue. And just to anticipate the problem, what is the problem? The problem of prediction. We will talk about models, climate models, to make predictions of future climate. These models predict a lot of variables like temperature, rainfall, etc. For some of them, they are quite reliable. Temperature, they are quite reliable. For rainfall, it depends on the location. Rainfall in Bologna is not really predicted well by climate models. So this is why water boards come to us and say, hey, how can I make a prediction? Because if I rely only on climate models, it looks like the future is better than the past. And this is unfortunately what happens with climate models for Bologna. If you look at weather prediction for the future, there is less risk of droughts than looking at the past. So it is not, for a water manager, it's, so they want to estimate precisely probability of day zero in the next 100 years, which is what they ask for. Because then they use the probability to put it into they know the vulnerability, because they know how much they are vulnerable. Sometimes they don't know fully, so sometimes they ask also for some elucidation on vulnerability, and they know quite well the exposure. And they are insured, by the way, for part of it. Because you understand, if you are a water provider, because they are mixed public and private companies in Italy, so if they get to day zero, they have to pay for the damage. Other questions? Interesting question, by the way. Okay. So you understand it is tightly connected with sustainability. Let me go back to the PowerPoint. And this is why I suggested you to get aware of what sustainability is, what are the terms of sustainability. And of course, when we talk about climate change, we know it's a problem. Why it is a problem? Okay, you may say that it's a trivial statement, It's a problem not only for the evidence of what may happen into the future, or it's not only a problem for the increase of risks that it may determine. It is especially a problem because, as I just said, it's a problem to estimate to what extent it is a risk for the future. It is a problem to make predictions. How will the climate behave? And as I just said, climate is a lot of things. It's temperature, but not only temperature. I mean, temperature in itself, okay, it's a problem, but it's less than a problem than lack of water, than increase the frequency of floods. It is, and it is a lot of things, climate. And to understand how they will behave into the future, it's not easy. And let me give you some examples. It's not my clock. Let me give you some examples. Glacier retreat, it's an evidence, and we don't need to spend time on it. And also, the water cycle is a problem. If we look at the water balance from the Po River, you see that there is a massive exchange of water from the underground, the atmosphere, and then back to the river and the underground. And there is a massive use of water in what is the area that produces about 60% of the gross domestic product of Italy. And if you get a problem in this water balance, if you get a shortage of water, it's the exposure related to this damage is really, really massive. On the other hand, we have variability. So if we look at the annual minima for the Po River flow, along with the regression line, you see a slight decrease. It's not really a huge decrease. You see some droughts in 1950, you see here, from 1940 to 1950, there is a down. And there are some droughts. This is just summer flow. Annual minima. There are some droughts in after 2000. By the way, the 2022 drought, it's the most relevant one in the full record. On the other hand, if you look at the regression line, it doesn't show over the whole period a real decrease. So it's not difficult to make an interpretation and to think at the future. And if you use a model, a mathematical model, to try to make a prediction, then the indication that you get, it's not satisfactory. And let me just check if here I have the animated version of this figure. Just 1 second. I am convinced. No, it's not here. Okay, no problem. What I just wanted to say now is that there is embedded in the overall tendency, there is a cyclic variability which is not easy to interpret, which is due also to the large-scale patterns of the climate. You certainly heard about El Niño, La Niña. They are large-scale patterns of climate that may last for several years, which may determine clusters of floods and droughts, for instance, cluster of heavy rainfall and clusters of low rainfall, which are called, by the way, flood-rich period and drought-rich periods. When we discuss in science about these periods, this cluster of anomalies, we refer also to the Bible. You may remember the story of Joseph with the 7 years of abundance and the 7 years of famine, because already at that time, they knew that there are periods of cycles. There are the cycles in the climate which determine periods where you have climate changes that then revert back. And an example of this is the recent multi-year droughts that occurred in Australia from 2001 to 2010. They experienced 10 years of shortage of rainfall in, I think it was in the west of Australia. And they made a lot of investment to desalinate water. They got equipped with a lot of desalination plants because, of course, the drought lasted so long that they were a lot concerned. And then what happened is that after 2012, they didn't have any more water shortage until recently. So after 2012, up to 2017-18, they didn't experience significant droughts and they never used the desalination plants. Another example is other multi-year droughts recently occurred in South Africa for 5 years, in California from 2013 to 2017. They had 4 years of droughts and then fortunately they recovered, and recently they had another drought last summer. So, I mean, there is this natural variability that on the one end, it's something that is part of climate, of natural climate. On the other hand, there is the big question. This natural variability is exacerbated by climate change, by human impact or not? This is the first question. So, okay, we know that sometimes drought occur. And so the question is, under climate change, under human-induced impact, this drought will occur more frequently or not? If you look at climate models for Bologna, it looks like they occur less frequently. But, I mean, there is uncertainty in that. Second question, this natural variability, is today still sustainable or not? Because in the past, we had less requirements in terms of usage of natural resources. Now we have a society that is broadly based on an intensive use of natural resources. Can we survive without energy or with less energy? No. In the past, it was easier. Even for water, it's the same thing. In the past, it was easier to deal with the water shortages because people were not used to have a day-to-day great amount of water. So indeed there are many facets of the problem, and you understand that a first way to adapt to the new situation is in a way to step back a little bit in our development, in our use of natural resources, but this entails a high social cost. And this step back should be equally distributed over the globe. I mean, it is for some country, it is relatively easier to step back. For other countries, they cannot step back because they never move forward. So it is a global problem that requires a global consultation, not only in terms of mitigation of climate change, not only in terms of CO2 emissions, but also in terms of societal developments, in terms of sharing the societal costs. And while if you ask the public, everyone is convinced that we have to fight climate change, on the other hand, when you ask individual persons to step back from their comfort, the percentage of people agreeing to that is really very, very reduced. And this is the problem more than the political will, because, you know, the politics follow the people. And at least in the democratic setting, the politicians have convenience to follow the people, to get voted by the people. So usually when they oppose to something, it is because they know that some moves would be unpopular and would undermine their visibility. Okay, so let's move forward with the slides. And some examples of unsustainable impacts of societal development. Intensive agriculture. Look, agriculture is responsible for the great majority of water uses. 70% at the global level, freshwater uses. Agriculture is the responsible of this. Why we talk about water, food, energy nexus? If you look at the lecture that I suggested you to read on sustainability, there is a section on the water, food, energy nexus. Water is needed to produce food. Water is needed to produce energy. And the two uses are not fully compatible. So when you listen from people saying, let's build a dam because it produces electricity and water for food, the two uses are not easy to integrate. And here there is a mention on that. And so the use of natural resources for producing energy, this is another example of unsustainable impact. And it became, I prepared this slide 2 years ago. In the last year, it became clear what kind of problem energy could be and what could be the societal costs. I mean, producing energy may turn out in a huge cost for society. And then there is, of course, the emissions of CO2 related to the human activities. Again, agriculture is responsible for a good share of emissions. And there are, in general, any human activity, even natural activities, entails CO2 emissions, but it's clear that there are some activities like energy production, like food production, which are responsible for a lot of emissions. Another belief that should be reduced in terms of its importance is the contribution of cars and the contribution of transportation. It's not a huge contribution to the human-induced CO2 emissions. It is, of course, significant, but the problem is not solved by leaving the car at home, and it is mitigated. But what is really needed is a strategy for energy production. We will not talk about it, and a strategy for water and for food production. Okay, now I'm not sure if I think we talked about the definition of weather and climate, so we can skip this. And this slide just highlights, but I already talked about this, of the importance of statistics, probability. Probability is a branch of statistics. Statistics is analysis of numbers in very poor terms, in very how to say, in very poor words. Statistics is the analysis of sample of data, samples of data. Probability is a way of doing that. Probability is a formal way of doing that. Estimating the probability of an event is a way to analyze a sample of data. Okay, and let's forget about the fact for now that probability can be also estimated without looking at numbers. I talked about perceptual estimation, but in any case, you look at information. Okay, so statistics can also be defined as organized analysis of information through numbers or through other kind of information. Okay, now this is the key, climate change attribution. And the key of the controversy, because let's emphasize that when we talk about climate change, we got into a bombed field. It is very controversial, and this is a problem, unfortunately. It is a problem that it's controversial because the controversy implies complication in the discussion, complication in the identification of actions. Why it's controversial? I wondered for a long about it. I don't really understand why, or I may have some explanations why. For instance, political implication, economic implication. Political implication because it's a global problem. So being a global problem, which cannot be fully resolved at the local level, it means that it requires an interaction between countries, a concertation, an international concertation. So everything that requires an international consultation, we know it's complicated and to some extent controversial because you talked about different political views. So for instance, we know that traditionally, but this distinction probably should be a little bit rediscussed, but traditionally the right is minimizing the impact, tends to minimize the importance and the impact of climate change, while the left is supporting strategies with more strength. Okay, and therefore it implies discussing about climate change implies a confrontation between different political views. So this may be an explanation. And the global relevance of the problem could be also an explanation, because some people talk about the survival of the species, of the human species, when they talk about climate change. They are convinced to talk about the survival of the human species. But actually, I don't understand why, when we talk about water problems, there is less attention to it. And water problems are a global problem. Of course, they have a local impact, but precisely like climate change, it's a global problem. And it's also a political problem. But still, it's not so. And also, it's a problem that is related to human development and survival of the human species. But probably because with water, there is less concern of possible tipping points. With water, there is the belief that the problems can be solved at the local level. Also, water cannot be moved. And therefore, it's not like CO2 that travels in the atmosphere. So there is less perception that with water, when talking about water, that China may make a global damage if they use water in a certain way. And there might be a lot to say about the differences in the Western world and the Eastern world about the water uses. But probably there is less concern because people may think that the effects are confined at the local level. But actually, this is not completely true. But still, water is less controversial. I think that in general, what I noticed is that individual people are more interested in monitoring weather rather than monitoring water. There is not much interested in monitoring river flow, not much interested in monitoring rainfall, while there is a lot of interest in monitoring everything is related to weather. So this may be a reason. Here you see a link on the two videos. Evidence for climate change is the one that we just saw, and the second link is the other one I suggested you to look at. And but the moral of the story is that it is a controversial discussion to attribute climate change. So I think there is no question, as I already said, that climate is warming. There is no question on that. But when we come to attributing this warming to natural causes rather than human causes, there is a lot of controversy. And this controversy cannot be easily solved by just saying that 97% of the papers are in support of one theory rather than the other. Actually, is not so well defined. The extent of this discussion, it's not so well defined by a number, and it's more complicated. It depends on the location. It depends. The interest in climate change depends on the location, depends on the local conditions. I think that we can stop here for today. And on this lecture, I think I will move forward next Monday, while on Thursday we will focus on probability through some computer calculations. Questions? Good. Thank you, grazie, and thank you to those who attended remotely.